Hi, I'm Guang, 50 years old. In this lesson, we'll be having the techniques and applications of definite integration. So we're taking a look at this example over here and trying to figure out what kind of different methods we can use inside here, or what kind of methods do we have to use in order to solve it. Since at the first glance, double integration over the region of d square root 2x minus x squared minus y squared over x squared plus y squared minus 2x plus 2 and then dx dy, where d is bounded by x squared plus y squared smaller or equals to 2x and 0 is smaller or equals to y, that is smaller or equals to x minus 1. At the first glance, this question, it seems unsolvable, since whether you have like a single integration and you only have y, or a single integration and you only have x, you can't solve it. So we have to use other methods in order to solve it. So what are one of the first things that come to your mind when you see something that looks like a quadratic equation? So of course there are things like factorization, or if you're a little more into integration, you might know maybe you can try changing it into polar coordinates. But if you try changing it into polar coordinates right now, you would realize you have r and r square terms, which doesn't seem right. But are there other ways to use the polar coordinates? And that is what we will be taking a look at right now. Firstly, we will have to know what this boundary looks like. So starting off with x squared plus y squared is small or equals to 2x. If you have learned a little bit of circle equations, this equation would probably not be that hard to draw. But in case you didn't know, what you can do is x squared, you move the 2x to the other side, so x squared minus 2x, and then plus y squared. So how about we add 1 on both sides, and this is what we have. So now, the first three terms, you can basically make them into x minus 1 squared, and this is your equation. So does this look familiar now? Since most of you will probably be more familiar with this form, where you have your centers, which is at 1, 0, and your radius of 1, alright? So our circle at first you have an entire circle over here. Okay, I'll just draw that out. So this is your circle, where you have your center point at 1, 0, alright, so which is the 1 mark on the x-axis, alright? So for this circle, what is so special about it? We do have another condition for the boundary that we have, right? So in the other condition for boundary, we have y is greater or equals to 0. Now y is greater or equals to 0, so it's definitely just limited to your first quadrant now. So not only is y greater or equals to 0, y is also smaller or equals to x minus 1. So y is smaller or equals to x minus 1, that means you can draw the graph for y is equal to x minus 1. So what is that graph for x minus 1, or y is equal to x minus 1? You will be having something like this, alright? So here is your x minus 1 square plus y square small or equals to 1, and here is your y's, if you just want to say the equation, it will just be an equals. Right, so this is the part that we're going to see, but which part exactly is the area that we're going to take a look at? So since you have y smaller or equals to, that means you'll be below this line, but above your x-axis, since y is greater or equals to 0, which means we will essentially be looking at this part over here, this little sector, you might say. Right, so now that we know what we are exactly looking at, so how can we solve it? Well, unlike many of the times where you will use polar coordinates, since most of the time using polar coordinates, you'll probably just directly use x is equal to r cosine theta y is equal to r sine theta. But in this case, how about we try something different? First, we take a look at this question. Now, what did I ask from the beginning? What do you think of when you see a quadratic equation? So, quadratic equation, normally if you're just doing it at school, maybe you'll use a quadratic formula to solve it, or you could find the completing square for it. Alright? Let's take a look at what happens if you try to use completing square here. So, in the numerator of an x, negative x squared and a 2x. So how about minus x, something where you will see your 2x, so minus 1 squared. But in your numerator, originally, you do not have this negative 1, which means you would have to add on a 1. Alright? So that is what happens when you use completing square on your numerator. Now let's use it on the denominator, where you have x squared minus 2x plus 1. So we could use one of the ones from your 2 to finish your completing square. So this is what you are going to see. Now, if you can quickly recall from just now, I did say this is not really your conventional, or whatever you like to use, kind of polar coordinates. And what I mean by that is, in this case, we will actually be using x minus 1 is equal to r cosine theta, and y is equal to r sine theta. Alright, so this will be the kind of polar coordinates we will be taking a look at for this lesson. Right, so what's so special about this kind of polar coordinates? In this set of polar coordinates, you will directly take your so-called new origin, or this is basically the center of your circle, to be 1, 0. Alright? Okay, so how about let's try to substitute in your new values. So in this case, you will be having square root. So negative r square cosine square theta minus r square sine square theta. If you can immediately recognize this form, you would be able to realize that this is pretty much a negative r square. Well, same goes for the denominator. R square cosine square theta, r square sine square theta, that would just be r square. So you have r d theta. Right, now how about we take a look at the boundaries that you will be having. Since now your origin, so-called origin, is actually the center of your circle. So your r is just going to be from 0 to the radius of your circle. What is the radius of the circle? That's just 1. So your r is from 0 to 1. Or more specifically, you could just write out the entire thing in order to not be confused. R is from 0 to 1. How about your theta? So theta, it will start from 0 and it will end at this angle over here. So that angle, since you do know the equation of this line, well, its gradient is 1, so you just find inverse tangent 1, well, you would easily get pi over 4. Alright, so these will be the values for your boundaries. I will just write them a little more separate to be clearer. Sorry about that. Alright, so let's continue to take a look at what could possibly happen. But this continue, you wouldn't really want to stay in this form, right? Since even if you put the r inside to make an r square, it seems pretty hard to solve. So why not? This theta would have nothing to do with this r. That means we could first solve your theta. And your theta would obviously be theta and then substitute pi over 4 and 0. So you will have pi over 4 integrate from 0 to 1 square root 1 minus r square over 1 plus r square. These are pretty much the same, but it looks nicer in this way. And then r dr. So let's take a look at it again. Can we still solve it? No, we can't. If we can't solve it, there are some different methods. For example, integral over parts, can you use it? Doesn't really seem so. How about substitution? Right? Substitution is one of the other ways that you can think of as, let's say, a last stage resort. So what is exactly going to happen in this substitution? Right, so we'll take a look at it. Now in this substitution, let's say letting r doesn't do anything. How about let's let this entire square root be, well, something, let's say t, for example. Now this entire thing is equal to t. So what's so special about it? Next, of course, we will have to find r in terms of t. Whether you want to find your dr or you want to find your r, which you will see something magical later. So let's change this from t in terms of r to r in terms of t. Well, first things is obviously you have to square on both sides. Then of course you multiply to the other side. Then you can pretty much easily see you could move this t squared to this side or the r squared to the other side in order to get r square is equal to 1 minus t square over, so this is a plus now, so 1 plus t square. Right, so this is what you're going to see. Well, of course, you can go ahead and square root, why not? But wait, you don't have to do that yet. How about try differentiating this, which you'll get 2r dr, and this is equal to, that seems a bit tedious to differentiate, isn't it? Yes, you can differentiate this directly using your quotient rules, but if you want to make it just a little bit more simpler, you can change it into 2 over 1 plus t squared minus 1. Alright, yep, okay, so you can change it into this form since you can have 1 plus, well, 1 plus 1 minus 1 minus t squared, right? So that is pretty much what you're going to use, and that is why you have a 2 over here. Right, so now this seems a lot more easier to differentiate since you just have to look at your denominator, which you will have 1 plus, 1 plus t squared, and then chain rule into 2t. So 2t times 2 would be 4t, but of course, don't forget, this is power of negative 1. Power of negative 1, there will be another negative, then at last your dt. Alright, have you found anything special about this yet? Not yet? Well, then you will actually realize that there is an r dr over here, which is pretty convenient, I would say. And next, of course, you have to know what is your range for t. So r, when you substitute r is equal to 0, it's a 1 over 1. 1 over 1, well, t is obviously 1. Then substitute 1, well, you have a 1 minus 1 there, so it is to 0. Alright? So this is the kind of substitution that you will have to make. Of course, for different types of integrations, you might have to try different types of substitutions. Maybe you just have to use one part of the entire fraction, maybe you have to use the entire thing. It's about trial and error if you actually have no idea. Or sometimes when you just see the type of question, you can already know what kind of substitution to make. Alright, so let's put these in. That means you have pi over 4, so if you realize 2, you can divide it to the other side, which you will just get another 2. So negative pi over 2, integrate from 1 to 0. Then this term here basically becomes t, while r dr becomes t dt over 1 plus t squared. Right, so this is what you are going to see. But of course, integrate from 1 to 0 doesn't look very nice. How about let's use a negative to flip that, since you already have a negative from your differentiation. So that means you will be seeing pi over 2 integrate from 0 to 1 t squared over 1 plus t squared dt. Right, now we're at this step. Can we solve it yet? Put t squared inside as a t cubed. Well, it doesn't seem very solvable just yet either. So, how about let's repeat the same thing? Well, we can do another substitution, but this time, you might want to think a little more. This substitution, are you going to let this entire thing be something else? Wouldn't really want to do that, wouldn't you? So, in this case, if you have learned about trigonometry, you would quickly realize that there is a 1 plus t squared. And what is a thing that can use 1 plus something squared to become another thing? That would be your tangent. Alright? So, tangent. Let's let this entire thing be another variable. How about let's try something other than letting your pretty much your entire integrand be something. So in this case, you look at the denominator. Now if you're familiar with trigonometry, then you can think of something that contains 1 plus something squared is equal to another thing possibly squared. So in this case, we will let t be equal to tangent phi, for example. Okay? So of course you can use cotangent, but well, that just depends on how you like to use it. And of course, maybe you want to use the same variable as before, but it's preferable not to do so since you wouldn't really want to confuse within the same question, alright? So, then you might again be wondering, wait, if you could use a trigonometric substitution over here, why not just use it earlier? You have to realize that in the earlier parts, you have a 1 minus something squared and a 1 plus something squared. It's not that convenient to use this trigonometric thing when you have multiple of the formulas that you could use, alright? So I have to be aware. But in this case, you just have 1 plus something squared, which would obviously be tangent. Right, so let's take a look at the t. Now, if you know this differentiation of tangent, that would be secant square phi, then d phi. How about the range of phi? So phi, when t is 0, so inverse tangent 0, that's still 0. How about when t is 1? So when t is 1, inverse tangent of 1, that is pi over 4. Right? So this is the substitution that we are going to make. Alright. So pi over 2, integrate from 0 to pi over 4. T squared, that means it is tangent square phi. Now what is the exact reason we use tangent? So if you know about trigonometry, 1 plus tangent square would be secant square. So secant squared would be secant to the power of 4, then phi, alright? So this is why we are in the denominator. But of course you can't forget your dt. So dt, you have another secant square phi, and then d phi. Right, so this is what we are going to see. Of course, you could simplify phi square, and since you have a tangent square phi over secant square phi, and tangent is essentially sine over cosine, or secant is 1 over cosine. So once again, you could continue simplifying it. And what should be the form you see after you simplify it? Well, that form obviously should be sine square phi, then d phi. But again, if you're not familiar with trigonometry, you might be stuck at this portion. So what exactly do we use here again? Well, we'll have to use your double angle formula. But you might have heard of two types of double angle formulas, for sine and cosine. But in this case, it will pretty much obviously be for cosine if your familiar with trigonometry. So you will be seeing pi over 2 integrate from 0 to pi over 4. So sine square, that means you have 1 minus cosine 2 phi over 2, and then d phi. Right, so now we will separate this into two different integrations. The first integration you're going to have is pi over 4, since this 2 you can just take outside. So pi over 4, integrate from 0 to pi over 4, you will have d phi. Or for the second one, you have minus pi over 4, integrate from 0 to pi over 4, cosine 2 phi d phi. The first one will just be phi. So you're going to have pi over 4 times pi over 4, which is pi square over 16. Well, for the second one, it's just going to be minus pi over 4. So cosine, but you have a 2 phi, so that means you need to halve it and get pi over 8. Cosine integration is sine. So sine 2 phi, then substitute in 0 and pi over 4. So your answer will be pi square over 16 minus pi over 8. But of course sine 0 is 0. So this will be the answer that you're seeing. Of course you could choose to combine them, maybe factorize a pi, but that's up to you and up to what the question wants. If the question gives something like a times pi over 16, whatever, it just depends on whatever you need. Alright? So this will be the final answer you get. Right, now let's make a summary of what we just had. From the beginning, we took a look at what this boundary looks like, where it is just a sector of a circle with a center at 1, 0, right? And then we use completing square within your integrand to get a familiar form, which you can use to change into polar coordinates. For this change into polar coordinates, you have to realize the center would actually be at 1, 0. So instead of having to substitute in x and y, you could just immediately think of the center as a new origin kind of thing. So then you could determine your boundaries, you could solve the part with theta, and in the first part, you used a substitution in order to try to simplify it a little more. Since this substitution seems pretty interesting, it manages to simplify it to allow us to use another substitution, which this time it is trigonometric. But of course, trigonometric substitutions, there are 3 main different types, and you would have to be familiar with all these forms in order to know when to use them. But other than that, it will just be some more simplification, use of a double angle formula, and more integration. Alright, so for this lesson, I hope that you are clear of everything that's here so far. Right, so we end this lesson here, and thank you for your watching.